जैसे वो मेरे रूम में आके मेरे लैपटॉप से बोल रहा है।
Prathamesh, please don't sleep in the class. Prathamesh, why are you sleeping?
Good afternoon, cadets.
Good afternoon, sir.
Good afternoon. Okay. Afternoon. So, both, yes, good afternoon again. Both divisions are here, right? This is because of Mali ma'am, because Mali ma'am says, I don't know about her problem. So, because of that, this combined lecture is there, and division one, your lecture is there at 4 o'clock now, right? So my lecture. So Mali ma'am will conduct that lecture. Okay. I think that message already given on our WhatsApp group. Okay. So just a minute, cadets. I will share this PPT, and all of you got the notes. Notes means basic electronics.
Yes, sir.
First part,
Yes,
first
sir.
part, right? Okay, and second part, I will complete that second part, and maybe on today or tomorrow, I will send that part also, right? So just a minute. Okay, screen is visible.
Yes, sir.
Yes, right. Sir. Right. Okay. So this part, that is again, I will directly start here because two divisions are here. So many cadets are joining till now, but these notes are already shared. So I think all of you, as per my thinking, you just go through these notes and clear your concept. Okay, I will just explain what is this. So the resistance of crystal diode. This part, I think not completed in last one, right? Only parameters, the maximum current, maximum power, that part. Yes. Because division, just a minute. Division 1, 2, 3. Right. You are lagging. Right. Okay. So resistance of crystal diode. This is the next part here as per the syllabus now. So very simple part here. Resistance of crystal diode is what, again, everything is written here. See, diode, if semiconductor diode is there, so obviously in forward bias the resistance is ideally zero. Resistance is ideally zero if the diode you are considering, that diode is an ideal diode. So obviously no resistance in forward bias, and in reverse bias infinite resistance is there ideally, right? But practically in forward bias some resistance is there, some resistance, that means very less resistance, maybe 5 ohm, 10 ohm or 15 ohm, depend on the doping and on the temperature or the semiconductor. That is again depend on manufacturing. And in reverse bias also, the infinite resistance is the ideal resistance of diode, but practically some very high value resistance is there in the reverse bias also. Okay, so this is actual part here. So ideal diode means forward resistance is zero and reverse resistance is infinite. Okay, but practically some resistance is there in forward bias and very high resistance in reverse bias, right? So just go through this one now. Forward resistance, the resistance offered by the diode to forward bias is known as the forward resistance. This resistance is of two types, namely DC forward resistance and AC forward resistance. See, cadets, diode, PN junction diode is there. So PN junction diode or crystal diode. So the biasing technique, biasing voltage means DC voltage. So obviously you have to apply DC voltage to this diode. Okay, anode is positive with respect to cathode, as well as in rectifier circuit you have to apply AC voltage also, right? That means this diode, so sometime the input voltage to that diode is DC or sometime it is AC. So because of that, there are two type of resistances. So that is DC forward resistance and AC forward resistance. Both type of resistance is there in diode. So DC forward resistance means what? Obviously, this point is written here. It is the opposition offered by the diode to direct current. Offered by the diode to the direct current. So direct current means what? Directly this much voltage is applied. So because of that, this much voltage will flow through that diode. So that is the direct voltage and direct current. It is measured by the ratio of DC voltage across the diode to the resulting DC current through it. Right. So DC voltage in this graph is what? OA. OA is a DC voltage because obviously this one is a forward voltage here and this one is a forward current here. That is a forward resistance, DC forward resistance. Right. So obviously forward resistance, DC forward resistance RF is equal to OA upon OB. OA, this one is voltage and OB is the current. So R is equal to V by I. That is our Ohm's law, like that. Okay. So according to that, this one is here. In that case, this one is a DC forward resistance of diode. Right? This one is the resistance of crystal diode. Forward resistance, under forward resistance, this one is a DC forward resistance. Right? The next point here is AC forward resistance. AC forward resistance. It is the opposition. It is the opposition offered by the diode to the changing forward current. To the changing forward current. So obviously, changing forward current means AC. Okay, that current is continuously changing. So because of that, that is AC forward resistance. So it is measured by the ratio of change in the voltage across diode to the resulting change in current through it. So this one is a graph here. OA voltage is there, then OB voltage is there, or OC voltage is there, whatever. This is a change in that voltage. Okay. So according to that, AC forward resistance RF is equal to change in forward voltage upon corresponding change in forward current. Change in forward voltage upon corresponding change in forward current. So obviously RF is equal to what? OC minus OA. See here. OC. OC and this one is OA. So OC minus OA, that means AC. The difference is what? AC. That means what? This one is here changing forward current. Changing forward current. So this one is AC. Okay. And same time here OF minus OD. So that is DF. So AC upon DF, that is a forward resistance, AC forward resistance of crystal diode. AC forward resistance of crystal diode. Right, cadets? Point is clear? AC forward resistance and DC forward resistance. Okay.
Yes, sir.
Okay. So let's go again the next
Yes.
slide. Just a minute. Yes, yes. Okay. So the next part, cadet, reverse resistance. Okay, reverse resistance, this part already explained, but this is the reverse resistance now. Resistance offered by the diode in reverse bias is known as reverse resistance. Okay. Ideally, reverse resistance of diode is infinite. However, in practice, the reverse resistance is not infinite because for any value of reverse bias, there does exist a small leakage current. This part already done in the VI characteristics of crystal diode or PN junction diode, right? So this is the reverse resistance of diode. So the in your syllabus, the point is written like this: the resistance of a diode, okay, like that. I think yes, resistance of crystal diode. So resistance of crystal diode means forward resistance, DC forward resistance, AC forward resistance, and reverse resistance of diode, right? These things are there. Okay. So in diode, the last part in diode, okay, that is equivalent circuit. So equivalent circuit, I think equivalent circuit means what? Simple circuit, simplest form of any device, like that. Okay. So equivalent circuit is a very easy circuit for our study. Means you have to design, you have to develop that circuit for our you have to develop means what already that design part is there, but you just go through that equivalent circuit, so that is very easy to understand the actual circuit, any circuit like that. So what is this equivalent circuit? See, that is an equivalent circuit of a device, an equivalent circuit of device, that is or example, crystal diode, transistor, etc., is a combination of electric elements. See, combination of electric elements which, when connected in a series, connected in a circuit, acts exactly as does the device when connected in the same circuit. That means whatever the electronic circuit is there, whatever the electronic device is there, you just convert that device in combination of electric elements, combination of electric elements. Okay. Once the device is replaced by its equivalent circuit, the resulting network can be solved by traditional circuit analysis technique. So that is very easy to solve that circuit. Whatever the numerical, whatever the design part of that particular circuit, that is very easy to understand, very easy to solve the circuit. So that is equivalent circuit. So the point written in our syllabus is equivalent circuit of a diode. Equivalent circuit of a diode. So just concentrate on this part, because I think there is no any explanation required in this equivalent circuit. You just concentrate here. Approximate equivalent circuit. This one is a diode. This one is a diode. So this one is diode positive. Sorry, anode is connected to positive terminal. Cathode is connected to negative terminal. Right. So obviously all of you knows about. Okay. First of all, I will read all these things. When the forward voltage VF is applied across a diode, it will not conduct till the potential barrier V0 at the junction is overcome. Right. All of you knows about that. V0 or VB voltage is required to conduct the that sorry, to switch on that diode. Okay, that much voltage is required. After that voltage only the current will start flowing through diode. When the forward voltage exceeds the potential barrier voltage, the diode starts conducting as shown in figure 1. So this is a current flowing through this diode, right? So if this diode is in forward bias, after barrier voltage only this IF forward current will flow through that diode. This is a basic concept, right? The forward current IF flowing through diode causes a voltage drop in its internal resistance RF, right? So what I'm talking here, the forward resistance of diode. Okay, forward resistance of diode is RF. Okay, so obviously some value is there. Some value means 1 volt, 2 volt, 3 volt, 4 volt, depend. Okay, 10 volt, 12 volt. That value will means that value is available in the data sheet of that particular diode, right? So that is the RF here. That is RF value. Therefore, the forward voltage VF applied across the actual diode has to overcome potential barrier and internal drop IFRF, because of internal resistance inside this diode, again voltage drop is there. That voltage drop is IFRF. So obviously you have to apply, you means in that circuit we have to apply the voltage, that means the addition of this barrier voltage and internal drop. Okay, so suppose here VF forward voltage is equal to V0 plus IFRF. For silicon diode, V0 is equal to 0.7, whereas for germanium diode, V0 is 0.3 volt. Therefore, approximate equivalent circuit of crystal diode is a switch in series with battery V0. In series with battery V0. V0 means biasing voltage. Sorry, not biasing voltage, barrier voltage. Right? V0 means barrier voltage. And the internal resistance RF as shown in figure. So obviously here, what voltage is required? See here now. This one is a VF. This VF should be greater than V0 plus IFRF. Greater than V0 plus IFRF. Then and then only the current will flow through this diode. So this diode is just like a switch.
Recording in progress.
VF should be greater than V0 plus IF RF. Then and then only actual current will flow through that diode. This point is clear, cadets, what I am talking.
Sir, can you repeat few points, sir, back?
Okay. See, okay. I will write here, no problem. See here. Okay, what I'm talking. See, V0 is equal to 0.7 volt. Okay. And because of this internal resistance of diode, maybe means what? This internal resistance is 2 ohm, 3 ohm, whatever. Okay, so because of that, the some drop is there inside this diode. That drop is what? IFRF. Okay, IFRF. That means, see, you have to apply this VF. So suppose this diode is just like a switch. This diode is closed. Okay, that means this voltage is given. Okay, diode is closed. That means some minimum current is flowing through that diode. Okay, minimum current is flowing through that diode because of this VF. Okay, but this VF at one particular point, VF. What? Yes. I'm not
Just
getting it.
continue. Someone was disturbing the class.
No, but there is no anything means. I think on my screen nothing is there.
Sir,
Nothing
Prathamesh is
there on
wasting
my-
the time. Na? Prathamesh just said that someone is wasting the. I don't know.
Okay, no problem. So I will just explain this one and then I will go for next slide. Okay, so 0.7 volt is here, and as well as you have to add this much voltage also, that is IFRF. So because of that, suppose 0.7 is this one, and IFRF voltage drop suppose 0.2 volt. Okay, 0.2 volt. This is my this is just for your information. Suppose this IFRF drop is 0.7, 0.2. So obviously 0.9 is the addition of this 0.7 and 0.2. So obviously you have to apply this forward voltage above 0.9. If this forward voltage is above 0.9, then and then only current will flow through this diode. So that is the approximate equivalent circuit of diode. Right? Okay. So I think the point is clear now. Right? Okay. So simplified equivalent circuit. So simplified equivalent circuit means what? Again, same part, but here internal resistance is ignored. See, for most applications, the internal resistance RF of crystal diode can be ignored in comparison to other elements in the equivalent circuit. Okay, that means RF value is ignored now. The equivalent circuit then reduces to the one shown in figure 2. So the equivalent circuit is just like this. RF is not there. Only RF is not there in this circuit, right? So this simplified equivalent circuit of crystal diode is frequently used in a diode circuit analysis. Here, right? So this one, see, just a minute, cadets. Okay. So this one is a diode again. IF current is flowing through that diode. This one is forward voltage VF applied here. Internal resistance is ignored. So because of that, this is just like a switch. This is just like a switch. And this much IF is flowing through that diode if this VF is more than barrier voltage of this diode. Barrier voltage is represented by this battery. Right. So this is simplified equivalent circuit of diode. Right. Ideal diode. Okay. Ideal diode model means what? An ideal diode is one which behaves as a perfect conductor when forward biased and as a perfect insulator when reverse biased. So obviously in such a hypothetical situation, forward resistance RF is equal to 0 and potential barrier V0 is considered negligible. It may be mentioned here that although ideal diode is never found in practice, yet diode circuit analysis is made on this basis. Okay, obviously the zero resistance is not possible, or barrier potential or barrier this barrier voltage or potential barrier V0 is zero. That is not possible in practice. Okay, but we are considering here this diode is just like a ideal diode, right? So because of that, therefore, while discussing diode circuit, the diode will be assumed ideal. See here, what is this? Because if any numerical part is there, in that case, while discussing diode circuits, the diode will be assumed ideal unless and until stated otherwise. That means if it is mentioned that diode is silicon diode or the germanium diode, then only you have to consider that much barrier voltage 0.7 or 0.3. Okay, so that is the important point here. Sir, we will be getting notes of this. Notes, these things are already added in your notes. Okay, and that notes already sent on yesterday and day before yesterday. Okay, so you just go through that notes, because this ideal diode model and equivalent circuit, everything is already added in that notes. Okay, 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 all right. Okay, Athav. Okay, just go through that one, right? Okay. So this is ideal diode model, and this one is the full part of that, means whatever the part till now explained. Approximate model. So approximate model means this one is barrier voltage and this one is the RF, that is forward resistance. So obviously this characteristic is like this. Okay. Simplified model, RF is not there, so obviously V0 is there, then your graph is like this. And ideal model means what? This graph will start from 0, because ideally there is no resistance, no forward resistance in diode. Okay, this is not possible, but ideally no forward resistance. So because of that, this one is a straight line like this. Okay, so these are the things which are required in this part, that is the equivalent circuit of diode, right? Equivalent circuit of diode. So these things are already sent in, means already added in that notes, right? Okay. So the next point, this is also a very easy part, and this is this point is already added again in that notes. Okay, photoelectric effect, thermoelectric effect, and the Hall effect. Okay. So I will not discuss about these effects in detail, because nothing is written like this application, and also because of that whatever given in my notes, that is sufficient for this study. Okay, just go through that notes carefully. Photoelectric effect, what is this photoelectric effect? See, from this diagram I think everything is clear. Whatever the electrons are here, if light rays fall on that material, then electron emission takes place. So that is photoelectric effect. So the simple application of this photoelectric effect is a solar, okay, solar panel. So that is the application of this photoelectric effect in short. Okay, so just read this one. What is this? When an electromagnetic radiation of particular frequency and above strikes a given metal, the photons from that radiation knock out electrons from the metal and provide them with a certain kinetic energy. This phenomenon, where emission of electrons or free carriers takes place with the transfer of energy from the photons, is known as photoelectric effect. So obviously here light rays falling on this one, and because of that these electrons emission takes place. See here, the photoelectric effect is a scientific principle that makes solar power possible. See here, solar power possible. The photoelectric effect is the principle referring to when electrons are released by photons, making an electrical current, which is what makes it possible for harvesting of electricity through the use of solar cells. So this is a basic idea about photoelectric effect. So photoelectric effect means whatever the things are here in this metal, if light rays of particular frequency is here, particular frequency strikes here, so obviously electron emission takes place. That electron emission means what? Obviously, you just convert that light energy or sunlight energy in electrical energy. So that is the solar. Okay, this is the solar power. So I think the idea is clear, clear from this explanation, right? So this is a photoelectric effect. Photoelectric effect, right? Okay. So I will go to next part. If any question, ask me, cadets. Okay, because nothing is there in this photoelectric effect, thermoelectric effect, Hall effect. So because of that, I will wind up fast here. Thermoelectric effect. So thermoelectric effect means of what? Obviously, thermoelectric means heat energy. Okay, see here. The thermoelectric effect is direct conversion of temperature differences to electric voltage and vice versa. Okay, so suppose temperature is given, output is electrical value or millivolt or EMF, and if EMF is given, then temperature is there. Okay, so that is the thermoelectric effect. The thermoelectric effect, direct conversion of temperature differences to electric voltage and vice versa. The Seebeck effect. Okay, Seebeck effect and Seebeck effect, Peltier effect, Thomson effect. So many things are there, cadets. Okay, and these things are there in thermoelectric effect. But again, all these things are not given in my slide or notes in depth, because again that part is there in your next year in control engineering or the other things like this. Okay, so I intentionally that part is not added here. Okay, because again it will take 15 to 20 minutes for all these effects, right? Okay, so the Seebeck, because in your syllabus only thermoelectric effect, this point is mentioned. The Seebeck effect occurs when the two ends of thermocouple. Okay, I think you know something about the temperature measuring device or transducer, that is thermocouple. Okay, otherwise I will explain that part also, right? The Seebeck effect occurs when the two ends of thermocouple are at different temperatures, which results in electricity flowing from hot metal to cold metal. That's all. This is the important point here, which results in electricity flowing from hot metal to cold metal. In the Peltier effect, a temperature difference is created between the junctions when electrical current flows across the junction. I will show you that. Okay. When heat is applied to one end of two conductors or semiconductors, heated electrons flow towards cooler one. If the pair is connected through an electrical circuit, direct current, DC current, flows through that circuit. Okay, this one, see, suppose this one is a cold surface here. Okay, here, see, this one is n-type silicon and semiconductor. This one is p semiconductor. So obviously current is flowing in this direction. See, suppose, see here, this one is heated surface. Okay, this one is hot surface. So hot surface to cold surface, current flowing in this direction. Hot surface to cold surface. So because of that, current is flowing like this. This one is a cold junction, this one is a hot junction, like that. One hot junction is there, but cold junction is there, and the current will flow from hot junction to cold junction, and that is known as thermoelectric effect. Thermoelectric effect. Okay. So in short, I will just show you what is this. See what is happening actually. Okay, because only by explaining this part, maybe just a minute, I will draw here something. To explain. Okay, one point is there, two metals are connected like this, and this one is the output of that two metals. Okay, so suppose heat is here. Okay, this one is a hot junction. Okay, and some temperature or flame is there or gas is there. Okay, like that. So this one is suppose chromale and this one is alumale. Okay, so combination of these two metals is here now. Okay, combination of these two metals. So this one is a junction of chromale and alumale. Okay, or chromale or nickel, like that. Okay, so because of that two dissimilar metals here, the current flowing through these two metals, and here your output is in millivolt form. Okay, millivolt form, DC voltage is there. So that is the thermoelectric effect. That means the temperature is input and output is electrical signal. Okay, output is electrical signal because of dissimilar metals are connected with each other. This is actual concept of thermoelectric effect. And suppose this millivolt signal is given here, so obviously heat will generate here. So that is a vice versa here. Okay, so that is a thermoelectric effect. That's all. Okay, because no any more explanation required in this part. Okay, so this is a thermoelectric effect. Right? I think the this part is clear, right? So
Sorry, you are muted.
Muted, sir.
okay. So you got these things or not? Because how this mute and all this things works? Just a minute, guys. Okay. Maybe sorry. Okay, so that diagram and all these things already explained. So is it clear to all? Okay, just see here. This one is heated surface and this one is cold surface. Okay, N-type material, P-type material. So heated surface to cold surface, electrons will move. Electrons will move like this. So because of that, electrical energy or the voltage generation here because of temperature. Because of temperature. Right, cadets? These things are clear or not? Okay. Electrons go where the energy is lower, so therefore it will move from warmer end to colder end, which leads to transporting energy and thus equilibrating temperature. Eventually, we can come to the conclusion that electrons on warmer end have a high average momentum as compared to the colder one. Therefore, they will, what is happening to, they will take energy with them more in number as compared to other one. Cadets, this effect is clear or not? Whatever explained now. Thermoelectric effect, this one is clear or not? That or can I draw that circuit diagram again? Circuit diagram means that part, what things already drawn here.
सर एक बार शॉर्ट में repeat करो.
ओके एक बार इन शॉर्ट बताता हूँ मैं, इन शॉर्ट बताता हूँ एक्चुअल में क्या होता है, बताता हूँ. जस्ट अ मिनट. म्यूट कैसे हो गया मुझे ही समझ में नहीं आया. ओके नो प्रॉब्लम. सो टू dissimilar metals are there and one junction of that two metals are here now. Okay, so this junction means suppose heat or temperature is applied here. Okay, heat or temperature is applied here. Okay, so because of this type of construction, two metals are there. Okay, normally this one is connected to, this one is hot junction here, and sometimes this one is cold junction here. Okay, and this is connected to one voltmeter like this. This one is a voltmeter. So because of that, see here what is actually happening. Because of this heat, electrons are moving like this. Okay, and because of the two dissimilar metals, this one is a cold junction, this one is a hot junction. So obviously temperature difference, according to that temperature difference, the voltage generation is there, because of this type of heating element and all. Okay, so because of that, the input here is heat or temperature, and output is millivolt. So because of that, this is a thermoelectric effect. So thermal, that means heat is there, and the output is millivolt here. Okay, this is in short the this is a effect. And because of that, this thermocouple is one very common device you are using for temperature measurement and control. Okay, so this one is a thermocouple. Thermocouple is like this. Two dissimilar metals are there, and its output is millivolt. Okay, so this is a thermoelectric effect. Clear, cadets? Now, means in short, the point is explained here.
Yes.
Right? Okay. Just go through this notes, because in notes everything is written. Right? Okay, but this is only for your information, and definitely these effects are there in your second year. Okay, because the actual application of these effects, Hall effect, and this thermoelectric effect, photoelectric effect also very important nowadays, because everybody is using now solar plant, and in that solar plant the basic concept is photoelectric effect. Right? So these two effects are there, and the another effect here is a Hall effect. Okay. So Hall effect, this one also sent on our group. Okay. So Hall effect means what? In short, again I will explain you what is this Hall effect using this diagram, because I think the diagram and explanation is very important. If a piece of metal or semiconductor carrying a current I is placed in a transverse magnetic field B, then electric field is induced in the direction perpendicular to both I and B. See here. This one is a current. This one is current flowing through that. Okay. This one is a current flowing through that, through the semiconductor, right? Because of this voltage, whatever the voltage is applied here. Okay. This one is a see here what is written. This is magnetic field B. So because of that magnetic, see, this one is X, this one is Y, and this one is X, this one is Y, and this one is Z. Suppose X is current, Y is magnetic field. So this one is the voltage. Okay, like that. See here, electric field is induced. Okay, so this one is the main part here. If current is passing through this one, magnetic, this one is Fleming's left hand rule, Fleming's right hand rule, I think. Okay, because that part is again required here, but it is not mentioned anywhere. Okay, so this is a Fleming's left hand. See here, this one is a Fleming's right hand used here. Okay, so according to Fleming's right hand rule or left hand rule, like that. Okay, so suppose current is this one, magnetic field is this one. So the direction of E, electric field induced, is perpendicular to both of them. See here, that is written here. If a piece of metal or semiconductor carrying a current I is placed in transverse magnetic field B, then electric field is induced in the direction perpendicular to both I and B. So this one is important. Okay. This one is current, this one is voltage, and this one is perpendicular to these two, So this one is the B, this one is current, and this one is see here, this one is voltage here. Right, so this one is electric field here, this one. Okay, see here, I think, see, basically this Hall effect is important effect to to know this used semiconductor material is N type or P type. Okay, so if electrons are going towards this surface, electrons are moving towards this surface, and more electrons are gathered here, so obviously that is a N-type semiconductor. And because of this effect, if holes are created and holes are gathering here, okay, to this surface, so obviously that is again a P-type semiconductor. See here, what is, I think that is written here. This phenomenon is known as Hall effect. Hall effect is normally used to determine whether a semiconductor is N-type or P-type, to find whether the semiconductor is N-type or P-type. Okay, same thing is okay, double typed here by me, okay, by mistake. So in this way, if that much current and that much the magnetic field is going to that particular conductor, so obviously the electric field is induced in the direction perpendicular to both current and magnetic field. And from that Hall effect, in my notes, that point is clearly added. So just go through that, because that point is not added here, because that is not much more important here. Okay, so this is a Hall effect. This is a Hall effect. Okay, so current and magnetic field is there, so the electric field is in perpendicular to current and magnetic field. This is the main part. Maybe question is there for 1 mark. Question is there for 1 mark, not more than that. Okay, 1 mark or 2 marks. What is Hall effect and what is the application of Hall effect? So application of Hall effect is to determine whether semiconductor is N-type or P-type. That's it. Right, cadets, just go through my notes, because that point is not added here, and that is very clearly mentioned in my notes. Right, Hall effect. Right, cadets?
Yes, sir.
Okay, just go through that, and if any doubt or any query, then I will explain it again in next lecture, but maybe everything is clearly mentioned in that notes, right? Okay, so here I will start one small topic. Small topic means that same again, basic electronics, but 10 minutes are there, so I will just ask you something about that topic, because that topic is very easy part again. That is the application of diode. Okay, application of diode. So very basic application of diode is a rectifier. Okay, and in our syllabus, half-wave rectifier and full-wave rectifier, these two rectifiers are mentioned. Okay, so obviously the rectifier circuit. Okay, rectifier circuit. So diode is a device which is used to convert AC form or AC voltage to DC voltage. Okay, AC voltage to DC voltage. So a rectifier is that circuit which will convert AC voltage to DC voltage, because on board ship or in so many plants also, okay, in industries also, the DC voltage is required in some cases. Okay, DC voltage is required. Suppose DC motors are there, or suppose you want to charge your mobile, charge your laptop, right? Because in your laptop battery is there. Okay, so battery means what? Obviously you have to charge that battery using DC voltage. Okay, or in your home appliances also, or suppose in your home inverter is there. Okay, inverter is there, or UPS is there. So obviously inverter and UPS means what? That is uninterrupted power supply. So if the actually the coming means, that is AC supply is coming in your house. Okay, and if that AC supply is not there, suppose because of some failure or electricity failure, AC supply is not there, so obviously one inverter is connected in that circuit. Okay, so when AC supply is there, so that inverter is in charging mode. Inverter charging mode means what? That DC battery is charging mode. Okay, that means how to charge that battery? You have to convert that 230 volt to 12 volt DC. 230, not directly 12 volt, 230 volt to 230 volt DC. Okay, that is only for your understanding. Suppose 230 volt to 230 volt DC. Say 230 volt DC battery is not there, but this is only for your understanding. Suppose 230 volt is there. Okay, So I will go in depth because 5 minutes are there now. Okay. So if your battery is of 12 volt, okay, battery is of 12 volt. So obviously you have to use what? Okay. If I want to convert, if I want to reduce 230 volt to 12 volt, 230 volt to 12 volt AC. So which device is required in that case, Candice?
Rectifier.
No. Rectifier is not there. I want to reduce AC voltage. I want to reduce AC voltage. 230 volt to 12 volt. Step down transformer. Step down transformer. Very good. Okay. So step down transformer is required. Suppose you want to charge your 12 volt DC battery. So obviously you have to convert, or you have to reduce 230 volt AC to 12 volt AC. Right. So here in this diagram, just see here. Suppose this one is 230 volt AC, 50 hertz supply is there. Okay. So suppose you are this load resistor. Suppose this load resistor is the range of this load resistor is 12 volt DC. Suppose. Okay. This is my assumption here. Or you just suppose this one is your battery of 12 volt and you want to charge that battery. Right. So obviously you have to use here one transformer. This transformer is what? Step down transformer. Step down transformer. Right. So this step down transformer will convert 230 volt AC to 12 volt AC. 12 volt AC. Right. This is not a DC voltage. Right. So at this point and this point means, suppose this one is 12 volt plus 12 volt. So this one is minus, like that. Okay. So this one is AC supply across this winding of this transformer. Okay. This one, A and B point. This A and B point is 12 volt AC in that case. Okay. So this one is step down transformer. Right. So this 12 volt AC voltage is available here now. And if you want to convert that 12 volt AC to 12 volt DC, I am not talking practically till now. Okay, practically. This is an ideal part. Okay, ideal part. Suppose 12 volt AC is here now. 12 volt AC is here now. Okay. So obviously, if you want to convert this 12 volt AC to 12 volt DC, right? So because of that, you want one device, and that device is known as rectifier. Clear this point now? This is a rectifier. So obviously, if you want to convert AC voltage to DC voltage, whatever the device is required, that device is known as rectifier. This is mentioned in your syllabus. What is rectifier? What is rectification? So rectifier means the device which will convert AC supply to DC supply. AC supply to DC supply. Right? Okay. Now, what I'm saying here, see, suppose this one is 12 volt AC. 12 volt AC. So 12 volt AC means what? Suppose this one. See, this one. Okay. 12 volt AC. This 12 volt AC is what? See here. This one is 12 volt AC. Total voltage is 12 volt. Total voltage is 12 volt. Okay. That means suppose this voltage is 6 volt and this negative voltage is 6 volt. Okay. Total voltage is 12 volt at this point. At this point. This one is 12 volt. Right. Now see what is happening in half wave rectifier. This 6 volt positive half cycle of 6 volt, positive half cycle of 6 volt is going to anode of this diode with respect to cathode. See here now. Positive half cycle means what? A terminal is positive with respect to B terminal. That means B terminal is obviously negative. Okay, because this one is a AC supply, right? So during positive half cycle, A terminal is positive with respect to B terminal. right? That means this negative voltage is at this point, and this one is the cathode of this diode, right? And positive terminal is at anode of this diode. So obviously this diode is in forward bias, right? Because as per our connection, positive terminal is connected to anode and negative terminal is connected to cathode. So obviously this diode is in forward bias, right? So because of that, the current will flow through this diode. Current will flow through that diode. That means during positive half cycle, this current will flow through that diode. During positive half cycle, current will flow through that diode. This is our first part, right? First part. The second part, I will just explain that part and then I will close this lecture. Okay. Second part, during negative half cycle, during negative half cycle. Negative half cycle means what? Obviously, terminal B is positive with respect to terminal A, right? That means terminal B is positive with respect to terminal A. That means the anode of this diode is negative and cathode of this diode is positive, right? So this is reverse bias. This is reverse bias. So obviously during reverse bias, no current will flow through that diode. No current will flow through that diode. So obviously this diode is just like open circuit. This path is not closed. So because of that, no current will flow through this diode. Okay, because diode is unidirectional device, so current will not flow in this direction. Current will not flow in this direction. So that diode is just like a off device in reverse bias. So because of that, during negative half cycle, no current will flow through that diode. No current will flow through that diode. Okay, because of that, this much gap is there. This much gap is there. Okay. Again, in next half cycle or next positive half cycle, again this will become positive with respect to terminal B. Again, diode goes in forward bias. Again, current will flow through that diode. Again, next cycle, next half cycle, no current will flow through that diode. Again, positive half cycle, again current will flow through that diode. Because of this, see, because of this rectifier circuit is known as half wave rectifier, because only positive half cycle is the output. During negative half cycle, no output is there. Positive half cycle, output is there. Negative half cycle, no output is there. So that's all. This point is clear, cadets, what I'm talking. So half wave rectifier means what? Only positive half cycle is the output. Okay. Our time is over, 4 o'clock. Okay. So this is a concept of rectifier circuit, half wave rectifier. Right? Okay. So this is our next part. So next time I will focus on this part, right? So I will close this meeting here, and division 1 and division 2 both CR. You just share your attendance of this class on our group. Okay. So I will close this here because Anand sir is here now. I will make him host and close this meeting. Right, cadets? Okay. Okay.
Yes, sir.
Right. So bye, cadets. Good day. Take care.
Thank you, sir.
Okay.
Yeah.
Anand sir, you are host now. Okay. And you continue now.
Yes, thank you very much, sir. I'll
Okay.
take over. Thank you.
Okay. Bye. Bye. Thank you.
Good afternoon, Division 2.
Good afternoon, sir.
I think we met in the morning. Some of you I met in the morning. Am I right? In the lab, physics lab. Who were there?
Not a division.
Not your division.
No, sir.
Due to what did you do in the morning?
Marine engineering drawing, practical.
The whole division.
Yes, sir.
Okay. So maybe it was division 1, I suppose. I don't know. Yeah. Or a 3. Okay, take a deep breath for 3 minutes. We'll begin soon. Today we are solving one more numerical, and that numerical I'll show you. Right now I can see there are 57 participants here, and I'm very curious how come there are 57 cadets here.
The earlier class was combined class.
It was a combined class, division 2 and which one?
Division 1.
1. Okay. So I think I encourage division 1 to leave, because anyway, if they want to be here, I don't mind. But I think they have something else more important to do. They have a lecture. Yes, it's not a free lecture for them. They are here only. They have a lecture. So I think they will soon leave. Just start thinking, everybody. How will you solve this problem? How will you find a support reactions of this particular truss? This is a truss with a overhang. What I mean to say is, at this very moment, it is fixed with the wall, vertical wall by 2 joints, and at this particular point, a downward force is given. apply rules of the equilibrium. Sigma of the forces is 0 and sigma of moment is 0, and find the support reactions and put them into the chat box. Come on, I expect few answers from all of you. Okay, anybody giving me the answer for this? We have 45 cadets still over here. Cadet Mohanty, are you here? Cadet Mohanty,
Yes, sir.
you are in which division?
One, sir.
You don't have your regular class over there?
Sorry, sir.
This is a division 2 I am teaching. How come you are here? Cadet Arshdeep, Cadet Arshdeep, are you here? Div 2, cadet Animesh. Cadet Ronak Bhadarka. (8043), are you here? Cadet 8043, are you here? Why do you take so much time to respond to me? Ayush Gehlot. Cadet Ayush, are you here? Abhishek Belgaonkar.
Yes, sir. I'm there.
Okay. Bharat Patidar.
Yes,
Bharat
sir.
Patidar.
Yeah.
Aman Kumar Singh. Cadet Aman Kumar Singh. Aman Kumar. Arunabh Gautam. Cadet Arunabh Gautam. Ayush Gehlot. Cadet Gehlot. Cadet Gehlot. CR. CR, will you please talk to me? CR. Who is the CR of this? Pardon?
Animesh.
Animesh, we have, what is the class strength? 35, right? What is the class strength? 34, right? So we have a 36 cadet present over here. Is Abhishek Belgaonkar in our division?
Yes, sir.
So who are the guests over here at this place?
Sir, last for Ankit
So I
Kumar,
guess this
Sagar
Dharma is not from our division.
Atharu Pandit,
Who? Sagar
Ankit
Sagar
Atharu Sagar.
Sagar and
Ankit.
Atharva are not from our division.
Okay, fine.
Atharva Pandit and Ankit Kumar. They are not of
Yeah,
our
okay.
division.
Sagar Sawant also. Okay, good.
Ravish Kalra also.
Okay, now we have 33 cadets. Somebody is still absent, but he will come. No problem. Okay, so now is there anybody who can give me the answer to this? What are the support reactions over here? Look, what is the analysis of the truss? We have been given a truss geometry and its loading. That is to say, all the dimensions are given and there only one load at a extreme point A, extreme joint A. And here there is a hinge joint and here there is a roller joint. As such, hinge pin is both the places, but here this is fixed with the wall and this is movable in a x direction. So first of all, our first job is to find out what kind of a support reactions we will be having. That was a good quote. Now you look at this. We have a this is a hinge support and this is a roller support. What kind of a support reaction it will provide? All of you know by now that hinge support can give reaction in a vertical as well as in a horizontal direction. And a roller support can give only one reaction which will be perpendicular to the surface which is on which rollers are moving. So we will be having these three reactions. Next case is we are showing this is a location 1. The joint I, of course, it is joint I, but I call it as a 1 to name reactions. So R1, reaction R1 has a X component here and a R1Y, Y component here. Location 2 has a only R2X, X component. There is no Y component here. So here we have to understand one thing, that these directions of a R1Y, R1X and a R2X, they are all assumed. R1Y can be like this also, this one can be like this also, or this one can be like this also. How we will know? We will know by two things. When you try to apply a equilibrium conditions, sigma of fx equal to 0 and a sigma of a fy equal to 0 and a sigma of a moment equal to 0, then you can have some inkling about the direction of the forces. Also, one thing is very clear, that if you assume a R1y in this direction and ultimately your answer comes R1y is equal to minus 16. Moment we get a minus sign, we know the direction that we assumed was wrong and R1 is acting in this direction. Okay. Are we sure about any other directions? Yes. This is a direction given and we know it is like that only. Again, at a point 2, there are rollers which are resting on a vertical wall and on which there is a hinge. As a result, one thing is sure, that this R2 is in this direction only. But about R1Y and R1X, we do not know. But we will come to know straight away when we consider force balance. For example, sigma of a forces in a y direction is 0. So here there are how many forces in a y direction? R1y and a 24. The positive y direction. So R1y minus 24 is equal to 0. So R1y is equal to 24. So this direction assumed is correct. So this direction and this directions are correct. We are still to find out about R1x, and that we will later see. Let us go to the further investigation. Here, how many number of members are here? First, let us check. Is m equal to 2j minus 3? Is this relation satisfied? What is the number
Yes.
member of a m? And it is what is the number of a j? Okay. What is m and what is j? M is a 15 and a j is a 9. So it is balancing properly. The truss is a stable and a statically determinate. Okay. It is stable and a statically determinate. Now, sometime what happens in some trusses, that some elements, some member which are neither in a tension nor in a compression, they have a zero force in them. Of course, I don't say that GF has a zero force, but in some trusses it happens that there are zero force members in the truss. Can you find out a zero truss member over here? There is one acting at this place, and we will just sketch it. Look at the joint E. At joint E, we have a R2X is acting in this direction. There is a tension or a compression in this direction. R2X is pushing in this direction. So ED must put at a point E, must push at a point E. In that case, sum of the X component is 0. Now suppose in a member EI, there is a tension and it is pulling the point E like this. Then there is no other Y component which is nullifying it. So sum of all the forces in a Y direction is not 0. So sum of all the components in a Y direction can become 0 provided the tension or a compression in this element is 0. Because R2x and a force in a ED, both are perpendicular to this. They cannot have any component to align in this direction and nullify ED. So force in a ED, this EI must be 0. So EI is a zero force element. It is a zero force member. If it is a zero force member, then it is not pulling I or not pulling E. It is not pushing I or not pushing E. It doesn't exert any force anywhere on any of the joints. So for the sake of analysis, it can be removed. So what we can do is from the truss, we are removing it only to make our calculations very, very quick. Right? But in the real life, EI is not removed. Though it is not taking a force, it has some other functions which we will study in a later on when we study a structural engineering, frames, etc. You will come to know about it. Now finding support reactions. To find support reactions, we have to apply these three rules. Moment we apply sum of the forces in x direction is 0, then we have a very interesting result. R1x plus R2x is equal to 0. R1x plus R2x, these two vectors on heading can become 0 only if both are 0 or R1x and R2x, they are in an opposite direction. Now we have seen earlier that R2x is in this direction only, so R1x got to be in this direction. And we are showing it in a direction which is exactly opposite to the direction of a R2x. R1x and R2x are in opposite direction. Okay. Now we go to the R1y. R1y minus 24 is 0. So R1y is 24 kilonewton. Very simple to find out. Now we take a moment about point E. This is a point E. Sum of all the moments about this point is 0. What is the moment of a R2x about it? It is 0 because R2x is passing through the line of action of R2x is passing through that point. Same way R2y. Its line of action is also passing through a point E. So their sum is 0. बचे only two forces, R1X and 24. Okay. The moment of a R1X about this point E is R1X multiplied by this distance, which is 1.5. That moment is in the anti-clockwise direction and a positive. Minus 24 into 4. So now we have a complete free body diagram, total truss and all the forces acting upon it. Here we have a 64 kilonewton, 64 kilonewton, 24 kilonewton and a 24 kilonewton. Now we come to the point A, joint A. Joint A, there is a downward force 24 kilonewton. Then we also have a force in a AF, which is either pulling or pushing, we do not know. Force in a AB, right? So I am showing that only with a is over here. Let us consider the balance of all the forces. We will be required to take cos theta and sin theta components. So what I have done is for this angle theta, of course it appears at many places. These are the values. Now look here. This is a joint A. 24 kilonewton force is acting downward. Why? Because it is given. Magnitude and the direction both are there. Now, sum of all the y component to be 0, force in a AF must be like this. Why? then and there a force 24 or a force of a 24 will not, will cancel each other. So AF is in this direction. If AF is in this direction, then vertical component is a AF sine theta and horizontal is a FAF cos theta. That is the reason we are showing it upward like this. Next thing to see is if AF is in this direction, then its x component will fall in this direction. So force in AB must be equal and also opposite to a force in this direction. If there is a force in this direction, then BA must be having a opposite and accurate group. Look further. Now, this FAF sine theta is equal to 24, and that will help us find out FAF, and then we can find out FAF cos theta. So working it out like that, we have this is FAF, this is vertical component of it, FAF sine theta, which is equal to 24. So FAF (28.8461 kilonewton). Then, once we find out FAF, then FAF will be having a component FAF cos theta, which is in a direction right to the left. So force in the AB should be opposite to it, direction B to the A. Here it is A to the B, here it is B to the A. So we get a value FAF is this much and FAB is this much. We now proceed further. Our analysis at a point A is over. Now, here we are focusing upon joint F. This circle is to be shifted over here, which I will do later. In this case, we have an exact idea of what is the force at this place. Direction of this place and direction of this place. FFA is known. It is acting at a point A, point F, like this. It has the two components. The horizontal component will be balanced by A. So we have a FFA cos theta and a FFA sin theta. If FFA cos theta is this direction, then a force in a GF has to be opposing it. If FFA sin theta is like this, then it must be opposed by having shown you this much. I think you can have a very clear idea about calculating the force in a here we can find out a force in a this and a this element. Then here you go. So this you already have Herbert, and we can have an idea about this a GF and a BF. Then you can come to the point B and can find out a force in a this and a this. Then you come over here and find a force over here and here. Then return to the point C and find a force in the CH and the CD. So I encourage all of you to find out if forces in all other directions. Let me tell you, cantilever trusses are used at many places. For example, they are in a airplane wing. In the bridge also, this is the cantilever part, and here also there is a this much cantilever, and here there is a this much cantilever, and this last end also is a cantilever. Now I understand that probably you will be having a clear idea about how to go about this. If you have any question, I would like to deal with you. Cadet Patidar, any question?
Yes, sir.
Biradar,
No, sir.
Biradar, any problem? Dougal, Cadet Dougal, no problem at all.
No, sir.
Okay, fine. So I'm getting this ready to send you, and you can send it. There are 10 minutes only have left. So what we can do is just now you can tell me this force is in this direction and this force is in this direction. This FFA is a 28 point, how much? Let us see. 8461. And tan theta is a 1.5. So find out cos theta and the sin theta and tell me what is FFA cos theta and FFA sin theta. Fast. I am waiting for the answer, sir. How much is this? Is anybody ready to write it in a chat box or no? I am sure you have your calci with you. Some answer is expected out of you. This is FFA. FFA is a 28.8461. Tan theta is a 1.5. Friends, now find out cos theta and the sin theta and tell me what FFA cos theta and what FFA sin theta is. Will you help me? Or this is not the way you would like to study? Cadet Biradar, Cadet Duggal, Cadet Bharadwaj, can I expect answer from you? Cadet Daksh Bharadwaj, are you here in the class?
Yes, I'm there.
Will you give me the answer about FFA sin theta and FFA cos theta?
I'm doing so. Just a minute.
Very good. Now Cadet Rilwani, Cadet Dev Rilwani, are you in the class? Dev, are you in the class? Cadet Tyagi, are you around? Cadet Tyagi, are you around here?
Yes, sir.
Have you found out the answer? FFA cos theta and FFA sin theta?
No, sir, I'm finding.
Does it really take this much time?
Excuse me, sir, I was speaking, but my mic was muted, sir. Oh, not
Who are you?
So Dev, sir, you called me, sir, and you didn't know.
Manthan Hatte? Cadet Hatte? Manthan Hatte?
He's sleeping.
Hatte, are
Yes,
you in the
sir.
class?
Yes, sir.
Have you calculated FFA
Sir,
sin
I'm
theta?
calculating.
How long does it take to calculate this? Do you want to say that such things disturb you, all of you, and we should not do this in the class? I should just keep speaking and you will listen if you want to listen. And you don't want to participate. I agree that participation is slightly difficult because we are not seeing each other. But if I ask you to do something, there must be a way to finish it up. Prathamesh Jadhav, are you in the class? Are you present?
Yes,
Prathamesh, do you have an answer ready with you?
Yes, sir, I am Prathamesh Jadhav.
Are you going to calculate this or no?
Calculating, sir.
Why do you take this much time? You don't know how to find out cos theta and sin theta with a calculator? Jatin Praveen.
Sir, I'm calculating.
Jatin Praveen. Jatin Praveen, are you in the class? Jatin Praveen, are you in the class?
There is actually with me.
Why is not replying?
Sir, my laptop, the mic is not working, so I came into this room, sir.
Okay, but you reply to me from there, wherever you are, isn't it? You are
So
sitting
the
where-
mic is not working in my laptop.
Okay, fine, but you are sitting somewhere else, isn't it?
No, sir, I was in my room, sir. The mic was not working, so I came into Abhishek's room. Hello?
Daksh, your answer is incorrect. But however, I admire that you calculated it. Dear friends, listen, we may get disconnected or something fine, but if you just keep listening and don't work with me, then it is a quite a frustrating experience for a teacher. When I'm ready with a question for you, I have done everything for you, and you have to just use your calci, then why are we not doing it? So far, just got a one answer. I don't want to take away your time of a break. But you must reply to me. Nobody is living today without replying it to me.
Cos theta 0.87.
I want to know what is this total value. Cos theta 0.87. That is wrong, my dear. If tan theta is a 1.5, what is a cos theta? You have a calculator. Do you know how to calculate it? Is it a problem to calculate a cos theta and a sin theta from a tan theta given using a calculator? Is everybody having a calculator with?
Root 29, 2 by root.
Pardon?
2 by root 29, sir.
Cadet, do you have a calculator with you? Do you know how to use a scientific calculator and find out cos theta and a sin theta? Or reverse thing, if you are told that sin theta equal to 0.36, then how to find out theta? Can you do that? What is your theta coming to? Okay, don't worry. Tell me who does not have a calculator, scientific calculator with him. Is there anybody, any cadet who does not have a scientific calculator? And if so, if you have it, then do you know how to use that?
Excuse me, sir. The answer is 0.37
Which answer is 0.37?
tan theta, sir. Oh, sorry, cos theta, sir. Cos theta.
0.37. My dear
Yes, sir.
child, you are wrong. I admire that you worked it out. Thank you very much for participating. But that answer-
28.83.
28.83 is what?
FA cos theta.
Cos theta can never be more than 1. Are you out of your mind? Can cos theta and sin theta be ever more than 1?
No, sir, I multiplied FA into cos theta.
Theta is
So
56.3.
Fa into cos theta, what it is? What is the cos
FA
theta
is
coming?
28.
Is theta 56.3.
Yeah, that is correct. Theta is a 56 point something. See, all these things are required. You have understood the concept and everything, but if you do not know how to make use of your calculator, then what will happen in the exam? Now, exams are not going to be online where you can open your book, hide behind your laptop, and just keep writing the answers, and everybody gets the 80%. Those days are gone now.
15.98 FA cos theta.
15 Fa cos theta. Yes, you are right. It should be
15.98.
no. It will come if you go to enough decimal point. It will be pakka 16.
Yes, sir.
And who are you?
Sahil Jagtap, 080.
Sahil 080. Okay. Sahil, now find out this Fa sin theta.
So 24.
Yes, you are right, Sahil. This is 16 and this is 24. You are absolutely correct. If FFA is at 28.8461, then FFA cos theta is 16 and this is 24. Okay. It is, see, it is a, some people might be finding it absolutely easy. And that is the reason they don't work. Why do this? And some people do not know or they just don't like working with the teacher. Now, can you go to the other joints and I can solve the problem further? Is it possible for you? Then I'm putting this into a, what we call, on our Moodle. Kindly work further on it and it is to be submitted.
Yes, sir.
Fine. Thank you very much to all those who were attending. Now let me take a snapshot of your attendance.
Can we leave the meeting?
Just give me 2 minutes more and then you can leave the meeting. Sorry about it, but I have to take a snapshot so that I know, because I know those who are here, they have understood, and there can be an issue with those who have not understood. Okay, make it clear that everybody will be sitting with a Kelsey and a paper with me, paper in all the online lecture. You sort out your problems of a line connection, etc. I am putting a complaint also, and you also be slightly forthcoming and present your case to the year coordinator or maybe to the vice principal and get your connections settled. And whenever I ask something, it is to be responded to immediately. Jatin Praveen, are you here? Jatin Praveen, look, this is what happens. Then why do you take? Are you sleeping? Why don't you respond to me that you are here? Yes, should come.
Mic is not working properly, sir.
Why it is not working properly? Why it is not working properly?
It's delayed, sir.
Huh?
I don't know, sir.
You
Seconds
don't know?
delayed, sir. When I turn on the mic, it takes 2 seconds to start it, sir.
Kindly set it right. About 3 minutes before I was calling you, didn't respond at all. Maybe somebody alerted you and now you are here. Okay, thanks for coming.
No, sir, no one's there in my room, sir.
Whatever. But earlier you didn't respond to me. You asked for revision. You are not the one. I'm not pointing out you. But such things keep happening, then you know it is not possible to grasp the subject.
Yes, sir. Okay.
Fine. Have a nice evening.
Yes, sir.
मीटिंग एंड कर दूं पोस्ट बना दे
भाई देख ले तेरी मर्जी भाई एंड कर दे प्रवीण एंड कर
कर दिया